and becomes easier and easier with more and more practice. So let's start with the questions on the pages attached to this lesson, not the supplemental problems. Does anybody have any other questions from anything in this section? All right then, there was a whole slew of supplemental problems. I don't remember the exact pages. Oh, there they are, pages 20 to 23, questions 1 to 9. We could very easily spend the rest of the class going over questions that you might have, so we can't afford to do that. We do have to move on, but let's spend some time going over some questions, and then I'll let you know when we have to move on. Does anybody have any questions from this section? Go ahead, Zebi. I didn't catch that. 2b. So we have 1 over 1 minus sine of x plus 1 over sine of x. We have to put these two fractions together using a common denominator. Everything's already written in terms of sign. There's nothing to factor. I don't see anything there that's recognizable as another identity. Like I don't see 1 plus cotangent squared of x. So all I'm left with are fractions. Now, if you have fractions, I talked about this yesterday with denominators, but if I had the following fractions that I was going to add together, you have to come up with a lowest common denominator, and the lowest common denominator is always formed by including all of the factors of each old denominator. So the example, I don't know if this is exactly what I used yesterday, but if I had 1 over 6 plus, I better not use 2, plus 1 over 8, let's just say, you know, a lazy way of finding a common denominator here is just to multiply the 6 and the 8 together. But then you end up with a bigger number than it needs to be, and that can cause more work later. Sometimes algebraically, everybody, if you end up choosing a, quote, bigger denominator than is necessary, it's not that your work becomes more difficult later, it becomes that you dig yourself into a hole that you just can't get out of. It's weird that that could happen, but it does. So when you take a look at the 6 is the 2 times the 3. The 8 is 2 times 2 times 2. So your common denominator here would have to include the 2 and the 3. Okay, so your lowest common denominator would have to include a 2 times a 3. And we're basically done looking at this. And now we can move on to the next denominator. My common denominator has to contain all 3 of these. But I already have a 2 here. So it's not necessary for me to put 3 more 2's. I put 2 more 2's. And the idea here then is that the 6 is included in the common denominator and the 8 is included in the common denominator. So every factor in each denominator needs to be represented. When you take a look at this, r minus 1 is the only factor. It's not r and 1 as factors because it's not r times 1, it's r minus 1. There's nothing you can do to factor that. And the same goes with this. There's a single factor. So how are we going to represent r minus 1 in the common denominator? We're just going to put an r minus 1. How are we going to represent r for the second one? We're going to do that. So this would be similar to me having 1 over 3 plus 1 over 5. There are no factors that 3 and 5 have, that 3 and 5 share. So the common denominator would have to be 3 times 5. That's what I'm getting at here, is the common denominator will have to be equal to 1 minus sine x multiplied by sine x. And try to remember that when you put together algebraic fractions together with a common denominator, everybody, you do not multiply out the denominator. You leave the denominator that you've created in factored form. That's important. I'm going to rewrite the question which I think is a good idea whenever you're working with rational expressions, just to space things out so that I can say, well, I'm going to multiply top and bottom of this by sine of x. I'm going to multiply top and bottom of this by 1 minus sine of x. Didn't plan ahead very well here. Which is, of course, something you would need to show on a written response question. So what I get for the top of the first fraction will be sine of x. And then I have plus what I get for the top of the second is 1 minus sine of x. I did something here that I seem to be kind of skipping some steps here. I don't want to say to you that it's okay to go from this original question to what I've written at the bottom of the screen. Because on a written response question, I think it would probably be better to have an intermediate step of sine of x over 1 minus sine of x plus 1 minus sine of x over sine of x. By the way, if there's anybody out there that is looking at this and saying, oh, we're kind of cross-multiplying, don't think that way. We're not cross-multiplying. Does that make sense so far? Okay, and on the top, we're going to simplify the top. Sine of x minus sine of x is 0, so we're left with 1 over that denominator. And that's the answer. That's all we can do for this question.
Does the 1 not matter in front of the...
Can you repeat your question, please?
Does the 1 in front of the sine of x not matter?
This one?
The 1 minus sine of x.
This one. Well, I mean, it matters. It's here. I'm not quite sure where you're going with this, but let me roll with it. It's here, right? You're not asking about this first one. 1 times 1 minus sine of x is 1 minus sine of x. So it does matter. It's written down as part of the numerator. But when you have sine of x plus 1 minus sine of x, you have 3 things now that are being added or subtracted. And the order in which you add or subtract things doesn't matter. So I can take that first sine of x here and subtract the second sine of x and say sine of x minus sine of x is 0, and then I have 1 left over. So maybe it will help if I write the final answer. This is the final answer. And in answer to your question, I think what you're getting at is this one is this one. It does matter. It's part of the answer. Never, ever think that when you get rid of everything that you're left with nothing. You have to be left with something. Well, unless there was also 1 minus 1, then you would put a 0. Have I answered your question? Okay. Other questions? Go ahead. 2C. Am I on 2 right now? Is this the question we're talking about? Okay. So this is a complex fraction. Let me rewrite it. It's called a complex fraction because the entire fraction, which is separated numerator and denominator wise by that red line, has a numerator that is complex. In other words, the numerator itself has fractions. And the denominator has fractions. And the quickest, simplest, most direct way to clean up a complex fraction is always to multiply the top and the bottom of the entire fraction by what I've always told students is whatever is needed to get rid of those little tiny denominators. And I can say to you now that that means you have to multiply the top and the bottom of this expression by really what the lowest common denominator of the mini denominators is. But I don't need to say that. I can say if I want to get rid of this tan x here on the top, in the denominator of the numerator, I need to multiply the top and the bottom by tan of x. But then I can take a look at the bottom, the denominator of the entire fraction, and see that it has a denominator within the denominator of the entire fraction. That mini denominator I'm thinking about is tan squared, and when I multiply the bottom by the tan x in green, I won't get rid of tan squared, I'll only get rid of one of those tangent factors, which means I have to multiply top and bottom by tan squared to accomplish what I want. What's going to happen here, don't forget, we have a binomial here in the numerator, so you're going to have to multiply this tangent of x, tangent squared of x rather, by the 1, and also by the 1 over tan of x. You have to distribute that. So when I multiply tan squared of x times 1, I get tan squared of x. When I multiply tan squared of x by 1 over tan of x, I think it should be obvious, but tan squared of x is tan of x, tan of x. We're multiplying by 1 over tan of x. You don't need to show this, of course. I'm just explaining why you're going to be left with tan of x, because that's going to happen and you're left with an extra tan of x. So then we have plus tan of x. This is going to be over 1, because on the bottom the tan squared cancels with the 1 over tan squared. And I would go out on a limb and say that this is not going to be the answer. And if it were a multiple choice question, I know it wouldn't be the answer. And you have to start digging around and asking yourself how you can rewrite this in a different way. When you have that pink sheet, everybody, and you're going through all of these things, at the end of any application of one of these things, you need to reevaluate your plan. Because right now I'm looking at this, and although there was, that won't work. Although there was nothing to factor to begin with, I can certainly factor this now. Now, do I need to write over 1? No. Okay. But I can factor out of this tan of x and be left with tan of x plus 1. Now, I don't know if that would be the answer or this would be the answer. It depends on who wrote the question. Can you tell me if one of those is the answer? It's the second one. Yeah. Very often we like to express our answers in factored form if we can. This is something, if you go on and take calculus with me next semester, we'll always say, you get an answer, make sure it's factored, because it's more useful in factored form. Any other questions? Go ahead, Makai. 3J. Okay. Yuck. Okay. So this is one that stops us in our tracks. And I can tell you that I think the likelihood you would ever see this on an exam in this course is slim. But Math 30-1 is not just to get you ready for exams. It's to get you ready for post-secondary, and it's also to get you ready for calculus, if you're going to take calculus next semester. This, in fact, I think you might have asked before. We had a question at one time in, I think it was in polynomials, where we had an expression that had 4 terms and we were expected to factor it. And I said, sometimes when you have a 4-term expression, and by the way, this is kind of polynomial, isn't it? It's a cubic polynomial, but it's trigonometric. When you have 4 terms, sometimes you should try factoring by grouping. So I am going to group these and rewrite it as secant cubed of x minus secant squared of x plus negative secant of x plus 1. And I know factoring by grouping is taught to you in grade 10, but it's one of those things that's kind of taught to you and it flutters to the ground and you don't even pick it up again until you have to, say in this course. What's important is when you factor by grouping and you pair, you make 2 pairs of terms, you make sure it's plus in between the 2 pairs. And then you factor a common factor out. So I can factor out secant squared of x here and be left with secant of x minus 1. And then you factor out, if grouping works, and it doesn't always work, but it will here, you factor out of the second pair whatever is necessary to be left with what you were left with when you factored the first pair. And I can factor out a negative 1 and be left with secant of x minus 1. And now what you've done, it's kind of an interesting way to look at things. Now what you've done is you've gone from something that has 4 terms to something that has 2 terms. This is a single term. Minus this, which is a single term. And there's something they have in common. They have a secant of x minus 1, so I can factor that out. And be left with secant squared of x minus 1. Now, I think secant squared of x minus 1 is equal to something. I'm thinking Pythagorean identity here. I may be wrong. And again, as I've already told you, I'm not intimately familiar with my Pythagorean identities other than the sine squared plus cos squared equals 1 identity. So I need to look this up. But again, you should have your formula sheet in front of you either way. Yeah, look at that. This identity that's kind of in the middle of your screen, 1 plus tan squared equals secant squared. If I subtract 1 from both sides, I get secant squared, and I think I know now where this is going. I get secant squared minus 1. So that means that secant squared minus 1, this is tan squared. Okay? So we get secant squared, we get secant of x minus 1 and then times tangent squared. I'm going to guess that that might not be the answer, or is it? It is. Okay. There's other things you could do with it. That's, you could take that mask off and start playing around with it. You could write the tan squared as sine squared over cos squared and multiply it in and see what happens. There's all kinds of things you could do. All right, we are going to move on now. That doesn't mean that we're done with this. We won't be done with this stuff until we're done with the course. But there will certainly be time in the coming days to practice more of these. We're going to be moving on now and looking at section 6.2 in your textbook, which is lesson 6.2 in your handout. And we break this lesson, or this section, into 2 parts. Textbook section 6.2 deals with sum identities, difference identities, and what are called double angle identities. And part 1, which is what we're doing today, are the sum and difference identities. So we're going to apply the sum and difference identities for sine, cosine, and tangent to find equivalent expressions. And then we're just going to do some work with them, whether it involves verification, whether it involves manipulation of identities or manipulation of expressions using these identities to come up with a simpler expression. Basically, everything we did with the 3 types of identities over the past few days, we're going to do with this. So to begin with here, I would like you to take a look at your formula sheet and just confirm that what I have up here matches the identities on your formula sheet. The reason I'm asking you to do that is I retyped this morning because my file got damaged and I didn't have time to double check it. I think these are correct. Well, I'm not asking you to think about what they mean. I'm asking you to verify that that's what's on your formula sheet. And I'm pretty sure these 2 are correct as well, but I would hate to have something in this presentation that's not. And they are. Okay, so again, I lost the file. It got damaged. I had to retype this thing in a rush this morning, and that's why I was not sure if they were the same. So, man, this is a lot to take in. you have these sum and difference identities. And first of all, what does it mean? What does it mean to say the sine of alpha plus beta equals sine of alpha cos of beta plus cos of alpha sine of beta? It simply means that if you were to take, I don't know, let's go alpha equals 20 degrees and beta equals 10 degrees. And I said to you, find sine of 20 degrees plus 10 degrees. Well, you know what? We know what this is. Because 20 degrees plus 10 degrees is 30 degrees, and you should know that sine of 30 degrees is 1/2 on the unit circle. When you go to 30 degrees, it has a y-coordinate of 1/2. So this, we know this is equal to 1/2. But what we're saying with this identity is that it can be found, and we wouldn't find it this way. This isn't the point. I'm just verifying that this identity works. It can be found instead by taking sine of 20 degrees times the cosine of 10 degrees plus the cosine of 20 degrees times the sine of 10 degrees. Now, I want to point something out that I think is interesting. Any one of these 4 trigonometric ratios is an irrational number. Sine of 20 degrees is irrational. It's not a fraction. It's not a fraction of integers. Cos of 10 is irrational. Cos of 20 is irrational. Sine of 10 is irrational. But when you put them together like this, you're going to get the exact same thing as getting sine of 30 degrees. So we can verify that, or I will verify it for you. I'm in degree mode. Not that it matters. It would still be true if I changed all those numbers from degrees to radians, if I just said 20 radians and 10 radians. But so it's sine of 20, cos of 10, plus cos of 20, sine of 10. Just double check my substitution. Looks okay. You get that. And again, if you were to figure out what sine of 20 plus 10 is, which is sine of 30, you get 0.5. This is the meaning behind these identities. And it is a way to, these identities are here as a way to simplify things. And we'll encounter lots of examples. I wouldn't recommend trying to memorize these. There's too many twists and turns. One of the things you should probably remember is that when you have the sine of the sum of angles, there's a sum of 2 terms. Sine of a difference is a difference of 2 terms, but cosine is backwards. So cosine of A plus B is cos A cos B minus sine A sine B. And then tangent is, I've never even gotten to the point where I remember these. I have to look every time. I would be too unsure of myself. So let's take a look at some examples. Write this expression as a single trigonometric ratio. So what you're doing here is you're looking for a pattern on your formula sheet in an identity that matches this. That's all you're doing to begin with. You're finding an identity that has sine of an angle times cos of an angle minus cos of an angle times sine of an angle. And the identity says that this is sine of A cos of B minus cos of A sine of B. Sometimes I will use the Greek letter alpha for A. Sometimes I will just use A. Sometimes I will use the Greek letter beta for B. Sometimes I will just use B. Okay, you should be adaptable. What are they on your formula sheet? Are they the alphas and betas? I think so, yeah. Now on your formula sheet, I hope you see how what I've written in brown matches the line above it. On your formula sheet, this is equal to sine of A minus B. I think. Yes? Don't just be a passive person in a seat here. Take a look at your formula sheet and confirm it. So that means since A is 42, since A is 42 and B is 19, I could color in the other 42s and 19s and A's and B's as well, but I don't feel the need to. This is going to be equal to sine of 42 degrees minus 19 degrees, which is 23. Am I right? Is it 23? So sine of 23 degrees. And again, we're into an area here where it's like, seriously, and I feel this way too, who cares? Well, I care because I'm trying to teach you that this identity is a way to compress things down. Because they're numbers, it wouldn't really be a great tool. You could just put it into your calculator anyway. But when we get to algebraic expressions, it becomes important. Any questions with 1a? All right. Now, I just have square brackets because when I do round brackets on my presentation, it comes out all blurry for some reason. So there's no difference, really. We've got cos 2 pi over 3, cos pi over 3, minus sine 2 pi over 3, cos pi over 3. And I believe in your notes this is a sine, isn't it? Okay. Let me fix that. So again, that's just because I was in a rush here this morning trying to type this up for our class. So do we see a pattern here that matches an identity that's known to us? Yes. Cosine, cosine, minus sine, sine is equal to cosine of the sum of the angles. The identity is cosine of A plus B equals cosine of A, cosine of B minus sine of A, sine of B. And that means we can add 2 pi over 3 plus pi over 3 together, which gives us 3 pi over 3, which gives us pi. And cosine of pi is negative 1. This is a good little written response question. Show that this is equal to negative 1 and explain every step. 2 marks. You're taking a known identity, you're comparing the identity to the question, you're simplifying the argument of the cosine to pi, and then you would also have to explain why the cosine of pi is negative 1. On the unit circle, cosine is the x coordinate, and when you get over to pi, you have an x coordinate of negative 1. I don't think it would be a written response, but I think it's kind of an interesting little written response. Number 2, determine the exact value for each expression. So this is an exam question. You would see this on an exam. The first thing to note is we want an exact value. And in the previous unit, you would be asked for stuff like, what is the exact value of sine of 4 pi over 3? Remember these questions? Vaguely. You would go to your unit circle. This is what I told you need to do. You would go to your unit circle and look at 4 pi over 3. You would say 1, 2, 3, 4 pi over 3. You would then determine the y coordinate there, which would be negative root 3 over 2. And the answer is negative root 3 over 2. And I noticed that when I wrote this up and I said find the exact value of sine of 4 pi over 3, 4 people in the room plugged it into their calculator. Because I did tell you, I suppose you could, go ahead and take sine of 4 pi over 3. You'd have to be in radians. And I think you should be looking at, when you put your calculator in radians and take the sine of 4 pi over 3, I believe you're going to be looking at negative 0.866. And some of us have seen that number enough times to go, oh, that's root 3 over 2. And I told you when we learned about the unit circle that I suppose you could lean on that crutch for the time being. But in the next unit, I said, it won't work. I'll tell you right now, if you take the cosine of 7 pi over 12, you're going to be faced with a number on your calculator. You have no idea what that number is. So you can't do it that way. Here's what we're going to do to begin with in this question. First, you're going to figure out how many degrees 7 pi over 12 is, because it's much easier to think in terms of degrees in these questions. So you need to figure out how many degrees 7 pi over 12 is. I would just take 7 times 180 divided by 12. I think I get 105. So I'm going under the assumption here that everybody knows this is 105 degrees. Well, that means we want to find the cosine of 105 degrees. Now, 105 degrees is a point on the unit circle, but I mean, every point is on the unit circle, but you don't know the x and the y coordinate at 105 degrees. It's not one of those 30-degree increments or 60-degree increments or 45-degree increments, but it can be expressed as the sum of two angles that we do know the coordinates of on the unit circle. I want you to find two angles that would add together to give 105, so that the two angles you choose are angles that we know the coordinates of on the unit circle. And the big hint here is that it ends in a 5. One of them has to be 45 degrees. So the other one would be 60? 60 degrees. So now this is cosine of 45 degrees plus 60 degrees. How is that in any way helpful? Well, it's helpful because the sum identity for cosine says it's cosine of the first angle times cosine of the second angle minus sine of the first angle, sine of the second angle. And these four things, cos of 45, cos of 60, sine of 45, sine of 60, are all things that you should know the exact values of. Now, could you use your calculator to cheat at this point? Sure. Like, let's say it's a written response question, and you don't know your unit circle, but you can get here. Well, you could use your calculator to find that the cos of 45 degrees is root 2 over 2. Well, you could use your calculator to find the cosine of 45 degrees and then recognize the number that's staring at you, 0.707, as being root 2 over 2. But, I mean, I would hope that you can go to your unit circle. I would hope that you can look at the unit circle and go, well, at 45 degrees, the x coordinate is root 2 over 2. At 60 degrees, the x coordinate is a half. I'm really going on an assumption here. I'm not going to be reteaching you the unit circle as we go through this question. I'm assuming that you understand that the cosine of 60 degrees is 1/2. I better make sure that's correct. Yes, it is. Sine of 45 degrees. So now we're looking at y coordinates on the unit circle. At 45 degrees, the sine is root 2 over 2. And at 60 degrees, the sine is root 3 over 2. And now we're going to simplify this. So we're going to multiply root 2 over 2 by 1 over 2 and get root 2 over 4. I'm amazed how many times people will write it over 2. They don't think that they should be multiplying those two 2's together. We're not adding fractions, you're multiplying them. You have to go 2 times 2 on the bottom. Minus root 6 over 4, which simplifies to root 2 minus root 6 over 4. And if you would have taken your calculator and taken cosine of 105 degrees, you'd be looking at a number. I'll show you the number. You would be looking at this number. There's no way you're going to know that that number is root 2 minus root 6 all over 4, but it is. Root 2 minus root 6 divided by 4 is that number. And this is a numerical response style question. I would never give you a multiple choice where this is here, because you could just put it in your calculator and see if it matches your calculator. So it would be cosine of 7 pi over 12. Was it 7 pi over 12, everybody? Okay. is equal to root A minus root B over C. What are the values of A, B, and C? 2, 6, 2. 2, 6, 4. Let's try another one. Tan of 165. So you need to break 165 into two angles that you know the locations of on the unit circle. Not just the locations, that you know the coordinates of the point of intersection on the unit circle. These questions always have a 45-degree angle. Because if you can break it into 30s and 60s, it will be a point on the unit circle that you're familiar with. So 45 and 120. This is tangent of 45 degrees plus 120 degrees. This is going to be a little bit more work. You're going to look at your sum identity for tangent, and I'm going to try to remember this. Is the sum identity for tangent, does it have in the numerator tangent plus tangent? Okay, then I think I have it. Your sum identity will have tangent of A plus tangent of B over 1 minus tangent times tangent over 1 minus tangent of 45 tangent of 120. Now, because tangent is not just an x or y coordinate, I would recommend determining the tangent of 45 as an exact value and the tangent of 120 as an exact value off on the side somewhere. Then we can put in the numbers. So what is tangent of 45 degrees? Well, I really hope that everybody knows it's 1. Because at 45 degrees, I can show you that section on the unit circle. This is the 45-degree intersection point. The x and the y coordinates are the same. And we know that tangent of theta is y over x, or sine of theta over cos of theta, however you look at it. Root 2 over 2 over root 2 over 2 is 1. So that's pretty easy. What about tangent of 120? Well, what we need to do is look at 120 degrees, divide the y coordinate by the x coordinate there. 120 degrees is here. The coordinates are negative 1/2, comma, root 3 over 2. So this is the 120-degree angle. So we're going to have the y coordinate, which is root 3 over 2, over the x coordinate, which is negative 1 over 2. Get rid of these pesky little denominators by multiplying the top and the bottom by 2. You're left with root 3 over negative 1, which is negative root 3. So now we're going to put those two things into the identity. Tan of 120 will be equal to tan of 45 plus, tan of 165, which is what we're finding, 45 plus 120, is tan of 45, which is 1, plus tan of 120, which is negative root 3, over 1 minus tan of 45 is 1, tan of 120 is negative root 3, 1 times negative root 3 is negative root 3, so we have 1 minus negative root 3, which is 1 plus root 3. And again, I hate to break it to you. This is an academic course, maybe one of the most challenging courses, even more challenging than calculus in terms of exam questions. I could have said to you on an exam, tan of 165 degrees is equal to a minus root b over c plus root d. Good luck just stumbling on that in your calculator by guessing and checking for a bunch of numbers. You need to know how to do this. Any questions with that set of examples? Go ahead, Jason. How did I get the denominator of 1 plus root 3? Oops. On the bottom of my identity, I have 1 minus tan 45 times tan 120. So the denominator here, the numerator is 1 minus root 3. The denominator is 1 minus tan of 45, which is 1, times tan of 120, which is negative root 3. So I'm multiplying here. I'm multiplying negative 1 times negative root 3. The negatives cancel, and I'm left with root 3. I'm sorry, I should have shown that step. Is that okay now? All right, let's take a look at a couple of others. Simplify this. Well, this is equal to cosine of pi over 2, cosine of x, plus sine of pi over 2, sine of x. I'm just applying the difference identity for cosine. But you know, well, I hope. See, now we're starting to rely on things you learned in the previous trig unit. You should know what cosine of pi over 2 is, and you should know what sine of pi over 2 is. Pi over 2 on the unit circle is the rotation angle that intersects the top of the unit circle, because pi over 2 is 90 degrees. And at the top of the unit circle, at pi over 2, the ordered pair at the top is 0, 1, and 0 is the x-coordinate, which is the cosine. So this is 0. Cosine of pi over 2 is 0 times cosine of x plus, well, sine of pi over 2 is the y-coordinate at that point of intersection on the unit circle, which is 1. So plus 1 times sine of x. Well, this is sine of x. 0 times anything, that is gone. That's not, we're not left with 1 there like the question that we were doing earlier that Zebi had asked about. It's gone. There's nothing there. And then 1 times sine of x is sine of x. And this, again, is a kind of a classic kind of question. So if I gave you tan of pi plus x, we can apply the tangent formula for the sum. And I think this will be tan of pi plus tan of x over 1 minus tan of pi tan of x. Did I get my identity correct? All right. Well, what's tangent of pi? Tangent of pi is 0. The reason tangent of pi is 0 is at pi radians, the ordered pair for the point of intersection is negative 1, 0. Tangent is y over x. Tangent of pi on the unit circle would be y over x, which is 0 over negative 1, which is 0. Again, I'm sorry, we have to grapple with this, and we're going to have to grapple with it a lot in the final example that we'll get to in about a minute. The x here on the right-hand side of your screen is not the x in the question. The x in the question is the rotation angle. You just have to deal with it. By the way, we know, we don't even have to worry about 45 degrees. Tangent of pi is 0, so let's just put 0 in there, see what happens. You get 0 plus tangent of x over 1 minus 0 times tangent of x. Well, that's tangent of x on the top. It's tangent of x on the top, and it's 1 on the bottom. Because you're taking 1 minus 0 times tan of x. 0 times tan of x is 0. 1 minus 0 is 1. We don't even need to write the 1. Right? Tangent of x over 1 is tangent of x. Any questions with that third example? I think it was the third. Okay. So now, I will tell you right now that for this set of examples, most of the work will be done in A. Once we get the answers to A, we can get the answers to B, C, D, E, and F really quickly. Okay? One of the things I want to tell you is that I would like you to change E to cosecant of x minus y, not x plus y. So that's on the bottom line in the middle. Okay, I just want you to change it to minus in there. Yep.
Ours is F. Ours is F.
A, B, C, D. Yours is F. Okay, I need to pull up my note package and check. And again, I apologize for my having to redo this morning, but let me just double check. Oops. Oh, so there is no D. Correct? Okay. I want you to change F to x minus y. Thank you, Jason. So is this your E? I take it then this is G. All right, so F should be cosecant of brackets x minus y. So going back to my point here, we're going to have to put a fair amount of work into answering A, but once we get A done, everything else will follow. This question is all about, everybody, careful, deliberate, organized thought. Okay. One of the problems with this question is you have a statement here that cosine of x is equal to 5 over 13, and x is in quadrant 4. So the first problem we have to grapple with is that x in what I've highlighted is not x on the unit circle. That's actually theta. Right? And when you take a look at the second statement, tangent of an angle is 4/3 and y is in quadrant 3, the y in the statement I've highlighted in blue is not y on the unit circle, it's theta. The next thing you have to grapple with is that the two thetas are obviously different, which is why I'm using x and y. Now, if you want to find, let's go to our identity now and write out how we would find sine of angles x plus y. It would be sine of rotation angle x, cosine of rotation angle y, plus cosine of rotation angle x times sine of rotation angle y. Did I decipher the identity correctly from your formula sheet to what I have written up here? Good. Now, here is the very tricky thing that's going to require a lot of organization. Because sine of angle x is y over r. That's how we find sine of a rotation angle from the previous unit. cosine of angle x is x over r. Are you with me? Cosine of angle y, cosine is x over r. But the x here is not the same x as the x here. One of the rotation angles, and this is what you might decide to do on an exam to make your job easier, is to eliminate those x's and y's and just call the first rotation angle A. Because if you do that, and you're going to have to make a decision right now, a personal decision as to whether you want to do that, what this becomes is this, which is a heck of a lot easier and less confusing. It's still going to require organization. But the bottom line is, and I'm going to finish off my statement here, this will be a y over r because it's a sine. But here's what you need to do now. You need to find x, y, and r for angle A. And you need to find x, y, and r for angle B. And every time I prepare this unit, I want to change the x and the y in the question to A and B, but I don't because they don't do that on the diploma exam. Okay. So what we need to do is talk about theta equals x, or theta equals A. And we need to talk about theta equals y, or if you want, theta equals b. And for theta equals x or a, there's an x, a y, and an r. For theta equals y or b, whatever letter you want to use, there's an x, a y, and an r. And like I said, this is the bulk of the work here. Okay. So let's talk about the first rotation angle x, which I've put red A over top of. The cosine of this first rotation angle, I'm looking up here right now. The cosine of that rotation angle is 5 over 13. Cosine is x over r. That means 5 is x and r is 13 for angle A, or what was originally called angle x. Let's just walk away from that for a second. We know x and r for the first rotation angle. For the second rotation angle, which was rotation angle y, or if you want to eliminate that y from everything else that's going on in here, you could call it angle B. Tangent is y over x, and tangent of this rotation angle is 4 over 3. So we would say tan is 4, or y is 4, and x is 3. What have I just made a fatal mistake in doing? Farhan? Right, I didn't look at the quadrants here. It says that angle y, or angle B, is in quadrant 3, and in quadrant 3, these are both negative. Now, I would say to you that finding the value of r here is, literally like stealing candy from a baby, right? He's not even looking at me. Dumb baby. You can find r here. Go ahead and calculate r for me. Well, how many of you don't have to calculate it? You know this combination of numbers. It's 5, right? Can you do me a favor? We're using x squared plus y squared equals r squared. Do me a favor and calculate y. What do you get, Evan? 12? Yes. Okay, good. You get y squared equals 144, so y equals plus or minus the square root of 144. Y equals plus or minus 12. And since it's in quadrant, I'm assuming it says quadrant 4? No. 4? In quadrant 4, x is positive and y is negative. See, now we can answer the question. you can choose to write this wherever. I'm just going to save time here and space and say sine of angle A is y over r, so it's negative 12 over 13 times cos of angle B, cos of angle B, which is y over r, but now I have to look over at angle B. So this was y over r for angle A, now it's x over r. This is the thing I'm talking about, organization and careful thought. It's x over r, but I have to look at angle B, which is negative 3 over 5, plus cosine of angle A, which would be 5 over 13, x over r, times sine of angle B, which is negative 4 over 5. Sine is y over r, and it's angle B. And then we can clean that up. When you multiply these first two fractions, you get 36 over 65. When you multiply these two fractions, multiplying across the top, you get negative 20 over 65. So we can put those together. There's a common denominator of 65. So this is 16/65. By the way, down at the bottom of the page, one of the questions that you're asked about is cosecant of x plus y. Correct? Is one of them cosecant of x plus y? No? Okay, we're not going to do E, F, and G. I wanted to have them match. I wanted to have a question where cosecant, we could just flip it over. But I've already messed that up by asking you to change something. So that's the answer to A. Any questions with the work we did here? Okay, so how are we going to do this? Well, this is cosine of x, cosine of y, plus sine of x, sine of y. I'm going to stick my neck out and just go by memory here. But I need you to follow along carefully and let me know if I'm right. Cosine of angle x is x over r, which is 5 over 13 for angle x, correct? Cosine of angle I, well, that's x over r as well, but I have to look at the second angle, and I believe it's negative 3 over 5. Sine of angle x is y over r. We're looking at angle x. The first angle, y was negative 12, r is 13. Sine of angle y is y over r. And for angle y, y is negative 4. It's horrible that they do that to you, or that I'm doing it to you, that we have y and y, but they're different y's. And then we have a third y for angle x. It's a lot to keep track of. We simplify this. This will be negative 15 over 65. This will be 48 over 65. I think negative 15 plus 48 is 33.